I never thought we'd see the day. No, I'm just kidding. Actually, I'm very proud to have Ross Mead defending his dissertation after not too many years. But Ross, as we all know, has distinguished himself not only in research but also in amazing outreach. So to actually have someone who has done so much outreach, K-12 and more generally in parallel with research is really amazing. The research is amazing. The research was competitively awarded with an NSF grant, basically, you know, based on, he does compliment me for hoping it gets funded, but it's his work. And he stood up to Faye Shaw and discussed it and got it funded with a National Robotics Initiative grant in his first year when the funding rates were very low. So this is all very impressive. It is only his intended career path that's disappointing at this point. But that's okay.
For us, but maybe not him.
No, it's like, well, it remains to be seen.
Right.
He may have a big
We'll
pivot.
see. I might come back.
Exactly.
For at least
It'll be a big pivot, yes. I mean, I have a postdoc open now, but I don't know about a year. No, anyway, so we look forward to the presentation, and congratulations so far.
Well, hi everyone. Thanks for coming to my defense. I'm going to be talking about proxemics and multimodal communication. To facilitate face-to-face interactions and human-robot interaction, a robot has to use communication mechanisms similar to that of people. So the robot has to speak through speakers and gesture using its own physical embodiment. It has to recognize speech and recognize gestures through its microphones and cameras. And typically the goal here is to meet the needs of the human user. However, these social signals, just like really any other signal, are attenuated by things like distance, orientation, and the medium through which the signals are traveling. And distance and orientation in face-to-face interaction is referred to as proxemics. And we actually have done some analysis of just how these signals are attenuated by proxemic behavior. I like to get to data on as soon as possible. So we can see that the robot tends to perform better in particular regions around here. So most of the work in human-robot proxemics showing human preferences of position relative to a robot shows that people want to be kind of close to a robot, between 0.3 meters and 1.3 meters. But we see that the robot performs best in terms of recognizing faces, hands, speech, in a range of about 1.5 to 2.5 meters. And so there's a discrepancy between what people want and what the robot needs. And so I want to kind of get across this idea that robots have needs too. Now, before I get into the contributions of this work, one of the main things that was asked of the committee during my qualifying exam was to create a video sort of highlighting everything that we're doing here. So I'm actually just going to kick it off with that, and we'll go from there.
At the University of Southern California, we are considering how an autonomous social robot should understand and use proxemics in human-robot interactions. Proxemics is the study of distance and orientation in face-to-face social encounters. Many studies in human-robot proxemics have shown that people tend to stand closer to robots than to other people, between 0.3 meters and 1.3 meters. At these ranges, the robot is able to automatically recognize human speech. However, the robot is unable to recognize human gestures because its cameras cannot see the entire upper body of the person. Thus, the robot often fails during an autonomous social interaction with a human user. In this work, we consider how the robot recognizes both speech and gestures in a face-to-face social interaction. The robot first imagines itself in thousands of different locations in a room. At each location, it predicts how loudly the person will speak and in what region of space the person will gesture. The robot then predicts how well it will automatically recognize speech and gestures and assigns a score to the location based on this prediction. Finally, the robot selects the location at which it predicts it will perform the best and moves to that location. Here, we see the robot predicts it will work well between 1.5 and 2.5 meters. The robot selects 1.7 meters as the optimal location to recognize human speech and gestures and moves there. Bannon, can you hear me?
Yes, I can hear you.
Bannon, can you see me?
Yes, I can see you.
If the average background noise in a room increases over time, the robot will predict that its automated speech and gesture recognition systems will not perform as well and will calculate a new location at which to interact. This work has been deployed on 2 different mobile robot platforms, the PR2 and the banded upper body humanoid atop an iRobot gave a mobile base. This demonstrates the portability of the approach.
This is to meet Maya's request for a dancing robot. You can see my glee.
And I can see your dance. I mean, your dance moves are not making it, okay?
Yeah.
Thank you.
There you go. By the way,
So scared.
this was edited last night for me looking happier in those videos. I was much more stern, I think, in the other ones. So, yeah, there's that. So at this point, that covers it all. You can all go home. It's all good for now. So that's basically a summary of the main kind of stuff that we've done here. And now I'm going to kind of break it all down. So the primary contributions of this work are a unifying framework of proxemics and multimodal communication that's grounded in the literature. Next, we look at human behavior recognition systems for recognizing proxemic behavior. Then we develop a data-driven probabilistic model for autonomous robot behavior generation, and then we consider objective, subjective, and behavioral evaluations of the controller. Secondary contributions are open source software systems. The 2 robots that you saw this running on, there were actually no changes in the actual proxemic controller that we'll talk about. It just ran on both of them, which was great, and also a large corporate data. So first, we're going to talk about the framework itself, and we're going to do this by considering some background work. So you'll notice after I introduce each contribution, I'm going to kind of give a contribution overview. I'll do this for every contribution in the presentation. So the goal here is to unify proxemic behavior and multimodal communication, and we want to make it so that the proxemic behavior is situated both in the interaction and in the environment, as opposed to just being these raw values that kind of don't tell us a whole lot of what's going on. We want this to be applicable in both human and human-robot interaction, and we want something that nicely can be applied to a robot through a computational framework. And so this is all a survey of literature, and we're going to try and bridge the gaps between existing approaches to try and come up with this unifying framework. So the way that people usually study this problem is looking at proxemics from a physical representation. So they look at distance and orientation and interaction. Now, what's nice about this is that this is a closed feature set. It's distance and orientation. The downside is it doesn't really tell you much about the actual interaction itself. So if I model the spatial relationships or the physical relationships between 2 people, and then I add a third person, I basically just have to build a completely new model. The original model does not extend to multiple people, so it doesn't tell us much about the actual interaction itself. It's not situated in the environment. So if I stand 1 meter away from Gigi, but I put the door in between us, this doesn't tell us anything. So it seems like a perfectly fine proxemic configuration. But this does extend well to social robots because we can measure distance and orientation during our interactions. Now that's the lowest level. At the highest level in background literature, people look at psychological features. So these could be things like psychological distance or these different sort of orientations, discretized orientation behaviors. So with psychological distance, it's actually very tough to turn this into a closed set of parameters. This is actually an open set of parameters. This can be things such as the amount of smiling, the intimacy of topic, the intimacy of thought, my arm configuration, the amount of eye gaze, et cetera, et cetera. It actually, the paper that introduces this literally has a ... at the end when it talks about this. So the parameters keep going. It's not a closed set of features. It is situated in the interaction. It tells us something about the relationship between 2 people. This tells us something about how people who are friends will stand closer than strangers stand to one another, and then people who are significant others will stand closer than friends. So that tells us a little bit more about the interaction itself. It's not situated in the environment, so if I had background noise or put a wall between 2 people, it doesn't tell us anything about that. It doesn't really extend well to robots simply because the notion of varying levels of intimacy with a robot is kind of a weird topic and not very well explored, and so I had no intention of going into that, and I don't know when people will. Someday they will, I'm sure, but not now. So what we're proposing is this sort of this middle ground. Now this is based on work from Edward T. Hall, who actually coined the term proxemics. He came up with these psychophysical features that talk about how we sense speech and gestures, how we detect smells and body heat during a face-to-face interaction. And this was in the 50s, and it was unanimously rejected because it was very hard to actually capture the data and talk about it. But since then, with modern sensor technology, we're actually able to do this. And so what's nice here is that it is a closed feature set. It's a closed feature set that's based on the senses of a person or the sensors of a robot. It's situated in the interaction, so basically it's telling us how the robot is going to perceive, or how the person is going to perceive these different social signals based on distance and orientation. It's situated in the environment, so it's telling us that if I add background noise to a room, it tells us how the positioning should change to compensate for the background noise. And it extends very nicely to social robots, because now I can take human perception of speech and make that as an objectively measurable analogy to speech recognition on a robot. So what's nice here is that this bridges the gap between psychological and physical representations. Here we can see that the relationship will dictate the desired sensory experience that people will manifest physically by moving, which then changes the sensory experience, which then changes the relationship. And so it bridges these two representations, and it unifies proxemic behavior and multimodal communication. So this is going to be sort of the grounding for the work that we do throughout the rest of this presentation. So next, we're going to talk briefly about human behavior recognition systems. So the goal here was to classify human spatiotemporal behaviors that indicate interaction cues. So we want to detect initiation of an interaction or transitions into the interaction versus termination of an interaction, which is a transition out of the interaction. What's nice for this is that if we have a group of people, the idea here is to be able to determine who the robot should be interacting with. So instead of trying to position itself with respect to everyone in the room, it might do it to a handful of people. And so what we do is we actually take the individual representations that we talked about in the previous slides, and we use those as features that we try and extract automatically from the data that we're detecting. Now this was talked about quite a bit in the qual, so I'm not going to go into this too much. If people have questions, I have extra slides on this that I can talk about. But really briefly, the first thing we did was a data collection. So we had two people in a room, and we were going to interact with each other and a robot. They were separated by a divider at the beginning, so they couldn't see each other. This sort of served as visual noise. Okay, and so the idea was that each person independently would approach the robot, and that would be our initiation. They would interact with each other and the robot for about 5 to 6 minutes, and they would leave the room, which was our termination. We used a prime sensor, which is like the Microsoft Kinect, to extract the locations of people. And actually, to our knowledge, this is the first study that was ever performed in human-robot interaction that actually used this sensor. This was well before it was released. Then from these data, we extracted these features. So we extracted each one of these sets individually. And we had these labels. Our labels were initiation and termination. And our goal was to train probabilistic graphical models, in this case, hidden markup models, to try and recognize either initiation or termination using each one of these representations. So we would try and recognize initiation using physical features, then try and recognize it using psychological features, then try and use it using psychophysical features. And what we wanted to do was compare the different representations. And our results show that the physical and psychological representations, it was about 50-50 in its ability to recognize it. And that was really because of this noise. These two different representations couldn't tell us anything about whether or not people could see each other, whereas the psychophysical representation could extract this pretty easily. And so here the idea is that psychophysical representation outperformed the physical and psychological. So that sort of gave us a little bit of motivation to continue using this representation for human-robot interaction. But it means that we have to build up models of how the robot perceives the world. And so next we'll talk about how we built up those models and use that for autonomous robot proxemic behavior generation. So we wanted to use our psychophysical models for human-robot interactions, and the goal was to model the relationship between proxemics and communication. And we're actually going to first focus on just that. So the process that we went through to do this, and here we model is a Bayesian network. So the model formalization, we assume that we have a human and a robot, and we have a set of model parameters. So here we have the pose of the person. So the question here is that we're answering is where will the human stand relative to the robot. Next, we have how the human will be communicating to the robot. So how loudly will the robot or will the person speak? In what region of space will the gestures happen? And then last, we have how the robot will be perceiving this information. So how will it hear the speech? How will it see the gestures? And we try to build up distributions over these parameters. So we're trying to figure out what the preferences of the human are when they're interacting with the robot. And then we would try to see how the position, the distance of the person to the robot influences how the human communicates to the robot. And then finally, we look at how the distance and how loud the person is talking or in what region of space the person is gesturing, how that influences the robot's ability to recognize these things. So we performed a data collection. It's a mixed 2x2 study where one condition dealt with the agent. It was either a human-human interaction or a human-robot interaction. And then the distance condition that's a within participants part of the study. We looked at natural distances and controlled distances. So the natural distances gave us the preferences that a person has for how they want to position themselves with respect to the robot. And the controlled distances tell us how people adjusted their communication strategy and then how that influenced how the robot perceived things. So each participant watched a short cartoon at these little stations. And when they were doing this, the reason we use cartoons is because that's a very common way in social science literature. When people are talking about cartoons, they tend to gesture a lot more. And so this is actually a pretty strategic thing to use cartoons here. And then one agent would move, either the human or the robot would move to this location X, and the other agent would approach to some distance based on the conditions. The first 2 times they would do this, they would actually approach to the natural location. So we get 2 examples of where they naturally wanted to stand with respect to the robot. And the next 4 times, they would move to one of 4 controlled distances. So they would either move to 5 meters, 3.5 meters, 2 meters, or a half a meter. And this was all displayed on their computer terminal here. And so we get a sense of where they want to be and how they might communicate at different locations and how the robot perceives it. So our measures, sorry for the gigantic picture of me, but our measures, we had microphones in the rooms and also on the robot and worn by the participants. And we use Microsoft Connects throughout the room to track their body at different locations. In each condition, we had 20 participants, and we gathered a lot of data. And so looking at the modeling of our data, comparing human-human and human-robot, we find that that actually people tended to stand closer, in this case to the PR2, than they do to other people. And in fact, it's consistent with a lot of work in human-robot interaction that people will tend to stand closer to robots than to other people. However, this is inconsistent with work that was done by Leila Takayama at Willow Garage, formerly Willow Garage, who actually found that people stood very close to the PR2. We're talking like a quarter of a meter. And this was primarily because the robot's arms weren't moving. So in this case, the robot's arms were moving, and so that might have biased people's distance to our robot. So we have this is our model for human preferences with respect to the robot. We can tell how people change their communication with respect to their distance. So in a human-human situation, as is also supported by related work, as the distance increased, the volume level of people's voices also increased. With respect to the robot, it also increased like that, but when they were very, very close to the robot, they actually talked really loud. And this is also supported by related work, where people perceive the robot's linguistic competence as being very, very low. And so they talk to it almost like they would a pet or a child. And so that was interesting. When it came to gestures at different distances, from a half meter to 5 meters, we actually saw no significant difference in the region of space that was occupied by gestures. And then last in our model, we look at how the robot perceived these things. And so we take all the information, put it all together, and we say, okay, at different distances, what is the likelihood of you recognizing speech or recognizing gestures? And we find, as you'd expect, up close, we recognize speech much better. But as the distance gets farther away, it starts to drop off pretty quickly. We use the Microsoft Connect for a lot of our tracking, and that doesn't work very well at detecting both the hands and the face until about 1.5 meters from the person, because you need them all in your field of view, as you can see over here. And so the idea here would be to try and find a nice balance between speech recognition and gesture production, which is what our controller does in the next set of slides. So that's how we model the relationships, and now we want to use the models to inform robot proxemic behavior in a face-to-face interaction. And so we're going to do this by sampling different poses in the environment to try and maximize the robot's ability to understand human communication. And then we're going to use motion control systems to try and get the robot to that location. So what the robot is doing, the robot is tracking the person here, and what it's doing is it's sampling locations. So it's picking these little dots, it's imagining itself at different locations, and it's saying, if the interaction happened right here, how loud do I think you're going to speak, in what region of space do I think you're going to gesture, and then how am I going to hear it, how am I going to see it, how are my speech recognition systems going to perform, and how are my gesture recognition systems going to perform. And then it gives a weight to that location, and you can see here it actually it selects the locations that that maximize its ability to perceive communication. So this right here, these dots all here are just sort of showing the entire space. This is actually doing importance sampling with resampling. And so what's worth noting here, and what we saw in earlier slides, is that the robot performance-based pose differs from the human preference-based pose. So it's actually different than what people want. And so that's going to be interesting later when we do our human evaluations of the robot. And so next, we have this goal pose. We have where we want to be. And so we give the goal pose to a robot motion control system. And so we came up with this simple reactive controller. The inputs to this are the desired and actual distances and orientations, which are encoded in the pose. And the output are the velocities. So again, you've seen this deployed on the PR2. We also have it deployed on Bandit and Ava in the lab. And this worked really, really well, but we noticed there were some weird cases where the system would actually fail. And what was happening was the robot was not considering its performance while it was moving. So as it's moving, it can end up in situations trying to get to the goal location where it actually can't track the person, or it couldn't hear the person. So for example, if the robot were directly behind me, trying to move in front of me, it would move in the shortest path, and while it's on its way, it would move through a location where it couldn't track me. And so the robot would just freeze in place. And so that's bad. We want to improve performance here. And so we took existing cost-based trajectory planner, and we wanted to weight it by considering how the robot would perceive the interaction. So you might see like this red line here is the reactive controller. This blue line here is showing us an unweighted cost-based trajectory planner. So this is planning our obstacle-free path to the goal, typically an optimal path. And then we weight this by what we call interaction potential. So interaction potential is basically this measure of what is the likelihood of having a successful interaction at any location along a trajectory. And so that would be something like this here. And so in this trajectory planner, we have a sequence of candidate velocities. So this is the velocity sampled at time t along the trajectory. And then the interaction potential, the likelihood of successful interaction of that candidate velocity, is the likelihood of it being able to perform a successful interaction at the next time step, so basically wherever that velocity ends up taking the robot. And so then the cost of that trajectory is the standard cost from the cost-based trajectory planner times the interaction potential. And basically, you could take any cost-based trajectory planner and use this. Here we actually took the ROS navigation stack, and we added a layer on top of that biased it by this. And so we have our different trajectories. We performed a small data collection in which I basically stood in the center of the pen in the lab, and the robot would move from these different locations here, always trying to get to the goal pose that our system predicted. And as it moved, we measured the path length and also the interaction potential along its trajectory. The path lengths were all normalized to the straight line distance from the starting location to the ending location. And so our results here, we have predicted, simulated, and measured for everything. What was nice is that we saw consistency between what we predicted, what we simulated, and what we measured. Simulated in gazebo, by the way. And so what we see here is that as we can expect, the unweighted cost-based trajectory planner gives us the shortest paths. Unfortunately, the interaction potential weighted cost-based planner has the longest paths, but it's not by much. And so we didn't think this was too bad. Really, the payoff you get is when you consider the interaction potential along the entire path. And so as it's moving, we see an unweighted trajectory planner is just trying to get there as quickly as possible and can track the person and hear the person almost never as it's moving along the path. The reactive controller does okay, but that's just sort of a byproduct of the keys that we selected. Really, the take-home here is that the IP-weighted cost-based trajectory planner significantly improves performance, often as much as 6 to 7 times that of a standard cost-based trajectory planner, which is really great for face-to-face interactions. And so just in summary, we model the relationships between distancing and also communication, and then we use those models to inform the design of our control systems. And finally, we're going to talk about the objective, behavioral, and subjective evaluations with human participants of these different systems. So first, we've already kind of talked about the objective evaluations. That was the performance of our motion controllers. So we're going to talk about the behavioral and subjective evaluations when we did these experiments with people. So a behavioral evaluation, what we wanted to do is manipulate proxemics and performance. We wanted to manipulate those in front of people. We wanted to see, do people naturally identify and adjust to the needs of the robot? And then our subjective evaluation, we wanted to see how proxemics and performance influence user evaluations. And so in this study, we artificially manipulate the performance of the robots as a function of distance. And then we're looking at changes in people's proxemic behavior with respect to the robot before and after the interaction. And then we also have user evaluations at the end with questionnaires. So we're going to go through the experimental procedure. It's a kind of a complex experiment, so hang on. So the idea here, we had a large room down the hall, and the idea was for the robot to move along this line to 10 different locations. So it looks like this. Yay. So the robot moves to 10 different locations in sequence, one after the other. And then at each location, a human, down here, the human participant, gives the robot an instruction to look at one of 4 boxes. So labeled square, X, circle, and triangle. These are just little boxes with icons, the big icons that we put on there. And so they would say, look at the triangle, look at the square, look at the X, just like this.
That is, look at triangle.
Yay. And so 10 locations, 5 instructions per location, total of 50 instructions given to the robot. And this will take about 20 minutes to go through. And what happens is the robot at each location gives either an affirmative or a positive reaction or a negative reaction, indicating whether or not it understood the instruction. And so that's like this.
That is, look at triangle.
So one of the things I'll mention is that we don't use speech here because we know that the speech of the robot will actually influence the positioning behavior of the person. And so we just use these nonverbal sort of affective sounds. Now there's also a negative example.
That is, look at circle.
So if you guys heard that buzzer at the end, it gets really, really annoying after you hear it about 50 times. Those are the positive and negative reactions of the robot to the person. And it's worth mentioning here that this is not the robot actually using live speech recognition and gesture recognition. If we did do that, then the claim could be that this is just a function of our speech and gesture recognition system. So what we did instead is we artificially manipulated the robot's performance as a function of distance. And as the interaction was occurring, the robot would basically predict whether or not, based on its performance curve, it would have actually recognized something. And so when a person pointed at a particular box or spoke about a particular box, the experimenter would press a button telling the robot what the person actually said. And the robot's trying to figure out, thanks for letting me know, but would I have actually recognized this had I actually been trying to do this live? And it would respond accordingly. And so, again, for a more general investigation, we manipulated the distance, the performance of the robot versus distance. And so this attenuated performance was approximated by a Gaussian. And then we parameterized this by 4 values. The first was the maximum performance distance, so where the robot performed the best along the line. So you can think of each one of these peaks as a separate condition, a separate between participants condition. We manipulated the maximum performance value. So sometimes people would see the robot work really, really well at certain locations, and sometimes throughout the entire interaction they would never actually see the robot work very well at all. Maybe it gets 1 or 2 of these things right at each location. We have the minimum performance. So some people actually saw the robot perform well all the time. So The robot would be interacting, and oh, it was great. The robot was always working. And so that was the minimum performance value. And then we also had the average performance across the entire interaction, all 50 interactions. And in this study, we actually had 180 USC students, completely, perfectly gender balanced, because I have awesome undergrads and undergraduate and master's students who helped me run this study and recruit participants, perfectly gender balanced. And it was a between participant study based on these parameters here. Also, I should mention that with 180 participants, this is also one of the largest studies that's been done in our field. So, our experimental measures, our behavioral measures, we measured where people wanted to be with respect to the robot before and after the interaction. We also extracted where they thought the robot performed the best. We actually asked them this after they give us their post-interaction preference. And we knew where the robot actually performed the best based on our performance resistance curve. And then our subjective measures, we had a questionnaire, which I'll go into in a little bit. So first we're going to talk about the behavioral measures. I'm skipping through 2 of the hypotheses. Again, if you'd like to know, I'm happy to pull up those slides. But here, our third hypothesis was that participants would adapt their proxemic preferences to improve the robot's performance. And so these were the data. Ignore the results right now. The first thing that we saw was that the data sort of go like this. It's sort of like a funnel instead of a nice smooth line like that. And if you're familiar with this kind of statistical analysis, you'll realize that this is suggesting that your data might be what's called heteroscedastic. It means that your variance is a function of the predictor variable. Okay, and that means that you often cannot perform traditional statistical tests like ANOVA, and often it's done, but it's bad and it hurts your claims. What's that?
Shouldn't be done.
Shouldn't be done. Yes. Okay. And so, sure enough, we did a test for non-constant variance, and oh no, we have heteroscedastic data, and so everything I know about statistics went out the door. And so. There are ways to resolve this. One of the ways that we used here is what's called a generalized linear model, which means that it separately models the variance and the mean. And so then you can apply related tests. And what's nice here is that we found that our hypothesis that people would adapt their proxemic preferences to improve the robot's performance was in fact supported, and very strongly supported. So what this is showing here is that the difference between where the person perceived the robot performing best and where they initially wanted to position themselves with respect to the robot, that right there predicted the change from after the interaction, from before the interaction to after the interaction. So basically, after they saw the robot moving, they interacted with the robot, they decided, you know what, if I simply move here over time, the robot is going to perform better. And so people naturally adapted their behavior to make the robot work better. And it was very, very strongly predictive of this, so we're really excited about this result. So kind of the takeaway here is that robots have needs too, and we've just shown that humans are willing to attempt to meet those needs. So that's an interesting implication moving forward. Now looking at our subjective measures, so again we had questionnaires, and the questionnaires tried to address these 8 different measures. So animacy, which is basically sort of how animated the robot is. Anthropomorphism, how human-like you might think the robot is. Competence, this is like the perceived intelligence of the robot. How much did you like the robot? How safe was the robot? How engaged were you during the interaction? How comfortable were you with things during the interaction? And also technology adoption, which is telling us something about the likelihood of people actually taking the technology and being willing to use it. So that's something that we really want to look at. And each one of these is a multi-item study, or a multi-item questionnaire, which means that we ask a lot of these questions basically many, many times in a different way. And then in the end we try to kind of match them up and say, okay, this is a very good measure of animacy or anthropomorphism. And so we modeled the data using bidirectional stepwise multivariate linear regression. And we found significant effects, which is a p-value less than 0.05, for 5 of the 8 subjective factors. In all of them, we found that the performance values, remember the values that we manipulated in our experiment, the average performance, minimum performance, and maximum performance were the most common predictors. And in fact, the location of where the robot performed the best wasn't predictive of anything. And we'll talk a little bit more about the implications of that later. So first, we found that the average, minimum, and maximum performance of the robot together were all predictive of the competence and likability as evaluated by the person. So this is sort of intuitive. It's people like robots that work. They like technology that works. Intuitive, but not very well quantified. So this is one of the first examples of simply looking at the performance of the robot and the impact that that's going to have on a human user. Likewise, we found that the average performance and the minimum performance were predictive of things like anthropomorphism, engagement, and technology adoption. So what this means is that repetitive failures are going to reduce people's evaluations. If they see the robot performing worse and worse over time, they're going to be done with it, even if it performs well on average. And maximum performance here is not going to really help you. Okay, so even if your robot works well a few times, they're not going to care. All they care about are failures over time. And so the goal here would be to try and avoid those failures. And so, in summary of our subjective measures, performance must be considered for a successful robot deployment. The average performance across multiple interactions rather than maximum performance in just a few interactions should be the focus of robot developers if we want to get these robots into the real world. We want to avoid user exposure to robot failure, our minimum performance, and so a proposed solution using what we have would be to have the robot use its models of its performance in different locations to predict its own failures and then preemptively act to resolve this. And actually, if you're interested in this stuff, talk to Michael over there, because he is doing some really cool work on failure. And then if we look at Proxemics, rather than performance, the maximum performance location was not significant at all. It didn't predict anything. So where the robot was, people didn't care, so long as the robot was working better. And even though it's not significant, that might be the most interesting result of all. So a lot of related work in human-robot interaction tells us that a robot that is abiding by, it's important for a robot to abide by social norms, in this case Proxemics, because it predicts their evaluations of anthropomorphism, likability, and safety. But we're basically saying that if that's only if the robot works flawlessly. So if a real-world robot is going to fail around people, then its performance is going to dramatically outweigh its need to abide by all of these social norms. And so in this case, we could actually say that performance is greater than Proxemics in terms of people's evaluations of our technologies. So a summary of results, just sort of put all these things together. Our subjective evaluation is telling us that performance, rather than Proxemics, is a more important consideration for acceptance and adoption of our social robot technologies. Our behavioral results are telling us that people are just naturally going to adapt their behaviors to accommodate the robot and basically gain the benefits of the robot. If you think about things like the personal computer, keyboard and mouse are not a natural human interface, but people have adapted their behavior to gain the benefits of personal computing technology. And with this, we're predicting that the same kind of thing will happen for personal robots. And then our objective evaluation at the end here is saying that our models and our motion control systems will objectively maximize, or at least attempt to maximize the performance of the robot in these interactions. So help us avoid failures, avoid user exposure to failures. So summary of quick contributions. We presented our framework based on psychophysical models of human and human-robot interactions. We used this for human behavior recognition and showed that these models actually outperformed related representations. We built up data-driven models for autonomous robot proxemic behavior generation. And then we were able to show that it outperforms, or it maximizes robot performance. People will naturally adapt to the robot and the robot that works. So secondary contributions, software is available open source, and our data are available upon request. Want to the sponsors. NSF. I want to give special thanks to my advisor for being here. Dr. Amina, hopefully watching on the live stream right now, and Edward helped with so many technical development things. My graduate undergraduate high school students, many of them are here, and then CS department. And last but not least, interaction lab members, old. And new. Couldn't be. And with that, I will leave this up and I'll take questions. So,
Okay,
stop it,
okay.
stop it, okay.
Secrets begin.
Just for the leaves, for the leaf remote.
Yes, yes.